Okay, so we're back. So what we're trying, silly. So what we're trying to show again is we're trying to decide, are these, uh, spelling guys, are these bases of R3? So do they represent all of R3? Now I have the invertible matrix theorem over here, and we'll talk about why it's over there in just a second. But this idea of the invertible matrix theorem is sort of clutch for describing pretty much anything that we want to talk about, and if it's possible, in any of our in anything. Like it's kind of like the catch-all of amazing at this point. I don't know. All right, so are these bases of R3? So if we take a look at this set here, so this is the set of 1, 0, 0, 0, 1, 0, 0, 0, 1. Hopefully you can see just by looking at that these things are all linearly independent, right? Essentially, this is, if we look at that, that is a matrix made up of the the identity matrix, right? That is the identity matrix. And so if I augment that, or if I let this be a x equals 0, hopefully you can very easily see that 1, 0, 0, 0, 1, 0, that this only has the trivial solution, which means that they are linearly independent. Right? The other thing is that I can use, if we think about this as, so right, this in the three-dimensional space, this first vector essentially describes a vector along the x-axis. And the second one here, this one describes a vector on the y-axis, and this one here describes a vector on the x-axis. In fact, this is, so yes, this is a basis for R3, and we call this a standard basis. So this is the standard basis. Okay? And it represents all of R3. Now, you ready for this? Here's where our invertible matrix theorem comes into clutch, right? Because, you ready for this? If I can show that any one of these things in the invertible matrix theorem is true, then I can automatically say that the columns of A are going to span all of R to the n. Okay? Now, each of these vectors is in Rn. So if I can show, you ready for this? If I can show that all three of those vectors are linearly independent, then I know that the columns of A are linearly independent, which tells me that the columns of A would span R sub m, which gives me my second qualification for it to be a basis, right? So for it to be a basis, we had to say that the columns, or all the vectors must be linearly independent, and the set needs to be equal to, or the space needs to be equal to the span of those vectors. Right? So here we go. So I have three vectors here that represents a 3x3 matrix. If I can show that they are linearly independent, then I can show that these things are, then I can say that this is a basis, right? Because I've satisfied 8 by showing 5, and both of those satisfy what it means to be a basis. Kind of makes sense. So the basis and the invertible matrix, so they sort of help each other, they sort of talk to one another, and they help support each other. But a basis and a matrix are not the same thing, right? So a basis is a set of vectors, but I can use a matrix made up of those vectors to tell me something about those vectors. Does that kind of make sense? Right? So basically the main things that we kind of need to show is if I set up a vector, or if I set up a matrix from my vectors, if I can show that the matrix has columns that are linearly independent, that means that my individual vectors are linearly independent, which also means that the columns there, or in other words, those vectors, their span represents all of R sub n, or R to the n. All right, so here we go. So what I'm going to do is I'm just going to set up my matrix, my 4, so 4, 2, 4, 4, 6, 2, 1, 8, -1. And all I need to show is that this is invertible. If I can show that I have no free variables, then all of the things in the matrix, invertible matrix theorem are true, and then I can say it's linearly independent and it's a basis. So I just need to do enough row reductions. So let's say if I can get this down to, and I can, so I can do enough row reductions to get me to 1, 3, 4, 0, 2, 3, 0, 0, 1. And even though this second column here, or this second row, even though that's not a 1 in that position, can you see that I have 3 pivot points? So there's a pivot position, there's a pivot position, there's a pivot position. That means that I have 3 pivots. So therefore, this is true, and this is true. So my basis here, I guess it would have been helpful if I named these as different bases. We'll call this one base 1, base 2, base 3. So therefore, my basis 2 is a basis for R3. All right. The last one, I'll let you decide that one on your own. So see if you can argue this one on your own and why that's true. But I will give you a hint that yes, this is a basis for R3. But come up with your own argument. See what you come up with. All right. So we got a couple more examples here for basis and what that means. Also, well, I don't know what's happening with my counting here. Just that should be a 1. I think in the notes that I uploaded, it was proper, but whatever. Maybe. Who knows? We'll see. So the invertible matrix term, again, it's clutch. So you'll notice here that all 3 of these things are bases. So these are all basis of R3. And they all have something in common. Now, something in common is they all have only 3 elements in the set, right? So from those 3 elements in the set, we can build all of space, basically. Or we can orient ourselves in any position in space from those 3 vectors, right? So the set of 3 vectors, its span will then build all of R3. That's kind of what that means. So it's the minimum number of things that we need in order to build all of the vector space. All right, so let's show, or let's verify, or let's argue that this polynomial vector space, so we've talked about briefly this idea of polynomial vector spaces, but let's talk about how this becomes a, oh, and I totally lost my train of thought. So let's talk about how this actually is a basis for the polynomial set n. So the polynomial set n says that in order to be in this set, I have to be able to describe, so this is described by any polynomial of t, needs to be some a0 plus a1t plus a2t squared plus all the way out to a sub n t to the n. And hopefully what you can see is that this, by definition, is a linear combo of all the elements in S, and that I can get any polynomial of degree n out of this equation, right? So absolutely any polynomial can come out of there. And then I can also get, and then this thing only equals 0 for the 0 vector, right? So if I can show that P of t equals 0 for only the 0 vector, which is true, right? So my polynomial is only going to be the 0 polynomial as long as all of these constants are 0. And there's no other option for that, right? Otherwise, I'm going to have a t in there somewhere if there's any number in any of those constants. So that tells me that that all of these things are linearly independent. And also, if you think about it, right, I cannot get, so linear independence or linear combinations just mean I can multiply, and I can multiply by a constant. So I can multiply one of those elements by a constant to get another one. Or I can add two elements together to get another one, or some combination of those two things. So each of these things has to be linearly independent, right? I cannot multiply t by a constant and get t cubed, right? I cannot multiply t by a constant and add it to some other t by a constant to get t cubed. So hopefully that helps you understand that those would be linearly independent. Therefore, S is a basis for P. So in other words, that set, the set of all of those elements, is a basis for P sub n. So for a polynomial of degree n, or a polynomial vector space. So here, this is the polynomial vector space of degree n, or the polynomial degree n vector space, however you want to call that. All right. So let's get into this idea of the spanning set theorem. So we're going to let S be some set of vectors that are in our vector space B. We're going to let our span of S equal H. If one of the vectors in S is a linear combination of the others, we can take that thing out, and the span of the new set will still be H. Right? So think about this. So if one of those is a linear combination of the others, then it doesn't change the span to take that out. So this idea of span, I think we need to expand a little bit about that. Span. So for example, let's say if I have the vectors, let's see, we'll do nice simple ones. So let's say S represents the vectors, I don't know, 1, 2, 2, 3, and -1, -2, right? Because I can get -1, -2 out of a linear combination of V1. So we'll call this one V1, V2, and V3. Because -1 times V1 is equal to V3. Those two things are not linearly independent. They are linearly dependent, right? I can use one to get the other. And what that tells me is that V3 would also be, so V3 would be an element of the span of just V1 and V2, right? Because the span, by definition, this is all linear combos of those vectors. And I don't need to explicitly state every single one of those linear combinations. So if I can show that one of my other vectors is a linear combination of the others, I can ditch it, and I can now express this as the span of a smaller set, and it still represents the same subspace, or it still represents the same vector space, right? second part of the spanning set theorem says that as long as my vector space, or as long as H is not the 0 vector, then some subset of S is a basis for H, right? So we talked about that the definition of H needs to be that for H to have a basis, or for S to be a basis, then it needs to show that the elements of S are all linearly independent, which we're going to do by taking out any of the dependent ones, and that still represents the same spanning set. And we've already defined that the span of S is equal to all of our H. So that makes this a basis. Hopefully that makes sense. Anyway, so let's do a couple of examples, and we're going to come back to this idea of column of A and the null of A. And unfortunately, I was thinking about defining these later, and they show up later in the notes. If you're curious and you can't remember what these are, and you want to go back to last week's notes, they are on page 6. Nope, let's try that again. Not 6. On page 9. The definitions for the null space and the column space are on page 9. But in other words, just because I forgot to include it, the null space of A is the set of all vectors, or the set of all solutions to the system AX equals 0, so to the homogeneous system, and the column space of A is the set that spans the columns of A. So this is the span of the columns of A. Okay. Now, a basis might mean that we need to take some things out of the span of the column of A in order to talk about that basis, right? Because the basis is the bare minimum of things that I would need in order to build the set for the column, for all of the columns of A. All right, so let's start off with some things, of course. So the first thing I'm going to do is, well, we need to go figure out how many, or we need to row reduce this, right? So this is equivalent to, so I'm row reducing this just as A. So A can be row reduced down to, where do I have it? 1, 0, 6, 5, 0, 2, 5, 3, and 0, 0, 0, 0. And the reason I'm doing this is to actually find us about the column of A. So the span of the column of A, so the column of A, so here, you ready? Okay. So the column of A is defined as the span of each of those vectors, right? -2, 2, -3, 4, -6, 8, and I ran out of space, so it's going to go below it, but it's still part of that span, right? So it's all the linear combinations of all of the vectors that make up the columns. However, we are asked about a basis, right? And a basis means I need the bare minimum of things. I have, it turns out, too many elements here. And because I do, right? If you take a look at these, turns out I have some linear combinations of each other. And I can prove that by showing that I have pivot points, or that I don't have enough pivot points, right? So what this tells me is that I only have 2 pivot points. So that means that these columns, or the columns here, these represent free variables. And because they represent free variables, that means that these are, well, not linearly independent. So these are, therefore, these columns are dependent. But if I nix them from my set, my spanning set, then I still have the column space of A, right? So even if I get rid of those 2 those two here, right? If I get rid of this one and I get rid of this one because they're redundant, so it turns out these are redundant in our span, right? My span still represents the same thing. So a basis, so the basis for the column of A is the set -2 to -3, 4, -6, 8. What that means is that I can build all of the column of A from these two sets alone. By two sets, I mean two vectors. All right. The last one is the null of A. For the null of A, we need to define our variables. So we need to take our lovely A here. And it turns out that if I take this A and I augment it with the 0 vector, any row reductions I would do to A without the 0 vector on the right-hand side are not going to actually influence. So this is equivalent to, I don't have to go back and redo all of our, or redo any of our row reductions. This would be equivalent, right? And what I need to do here is I need to write this into parametric equation form. So this tells me that that this one that says x1 is equal to, so here's x1, x2, x3, x4 is equal to -6x3 minus 5x4. Right, so and then the next one tells me that x2 is free. Nope, x2 is not free. Let's try that again, right? x2 is not free because I have a pivot position here. But I want to know what x2 is on its own. So I'm going to divide all those things by 3 and then rearrange. So this tells me that x2 is defined as, what is that? -5 halves x3 minus 3 halves x4. And last, as you can see, because these are free, that tells me that x3 is free and x4 is free. Free and clear. Now, we want to put this in parametric vector form because the null space is defined by the vectors is all of the vectors that make up the solutions to AX equals 0. So if I put this in parametric vector form, that says x1, x2, x3, x4, or in other words, every single x vector can be just defined by using just our x3 and our x4 variables. So x3 times -6 for x1, -5 halves for x2, itself, so 1 for x3, and 0 for x4 because x4 doesn't depend on x3, plus x4 times our -5, -3 halves, this time it's 0, and then 1. And our null space is equal to those two vectors. So I'm going to call this v1 and v2 just because I'm tired of writing them. So the null space is v1, v2. And this is also defined as a basis for the null of A. These things are automatically linearly independent, right? Because we had, obviously, it's just, they are. These are linearly independent, right? If they were not linearly independent, I could write this second vector in terms of x3, and I could write this first vector in terms of x4, right? They have to be linearly independent in order to satisfy this equation or satisfy this solution. So the basis for null of A is equal to the set of v1 and v2. Ta-da! Okay, we're going to come back, do one more example using the null space and the column space, and then we'll move on.